Today we will talk about a specific type of surface integral that describes the flux through a surface. And in order to understand what the flux through a surface means, we will think of our vector field F as representing the velocity of a fluid. Then the flux is going to be how much fluid is flowing across the boundary of some surface S. So our goal is to construct a surface integral that is going to represent the amount of fluid that flows across the boundary of a surface, and we call that the flux. So I'm going to draw a surface. And I'm going to label this surface S. And then I'm going to draw a vector field F that represents the velocity of a fluid. So these arrows represent the velocity of some fluid that is flowing. And I'm thinking about S as being kind of like an open surface so that water can pass through it. And what I'd like to do is I would like to understand, based on this velocity field, how much fluid is flowing across the surface. So what I'm going to do is I'm going to break up this surface into little pieces. So I'm going to break it up into little pieces, maybe about this size, and then I'm going to think about there being maybe just one arrow, one vector in my vector field F that represents the velocity of that fluid. So I'm going to enlarge that little piece. I'm going to call this piece here. I'm going to call it delta S. Okay, so this will be some small piece here, delta S. And I'm going to think about there being just one vector F that represents the velocity through that piece of the surface. Well, there's also going to be a normal vector through that piece of the surface. So we're going to call that normal vector N. And this is going to be a unit normal to my surface, delta S. And it's going to form an angle with F. We'll call that angle theta. Okay, so then we can ask the question, we're going to ask, what is the net flux through a small piece of the surface? We'll call it delta S. And that should be represented by the amount of F in the n direction times the area delta S. So we have the amount of the fluid that is flowing perpendicular to this surface, okay, times the area of that surface, representing the total amount of fluid flowing through that little piece of surface. Well, if we're thinking about n as being a normal vector, then this is just F dot n. That's the component of F in the n direction times, say, delta S. Another way to think about that is that's, say, the magnitude of my fluid velocity, okay, times the magnitude of n, which is 1, times cosine of theta. And if you look at the diagram, you can see that the dot product there does, in fact, represent the amount of f in the n direction, that of course is magnitude of f cosine theta, kind of decomposing f into the amount that's in the n direction. So that's the amount of flux through a piece of the surface. If I want the total flux through the entire surface, okay, then I can sum over all of the pieces. And I'm going to imagine that they're going to be indexed in 2 dimensions because it's a surface that can be described in 2 dimensions. So I'm going to imagine that they're going to be indexed there. And then I'm going to do the double sum of f, okay, over that small region dotted with n over that small region delta s. And then the idea is that if we let delta s get smaller, then things will get more accurate and we'll be able to more accurately represent the flux through the surface. Okay, so we're going to let delta s go to 0 to increase accuracy. Well, if I let delta s go to 0, we can see that this is a Riemann sum. The Riemann sum looks like the Riemann sum that we use to compute surface integrals. And so, in fact, this double integral that we're going to define, okay, of f dot ds, okay, in fact, will be the double integral over the surface of f dotted with the normal vector n ds. So here we're going to let f be a continuous vector field defined on a surface S, and it's going to have a unit normal vector n. So depending on where you are on the surface, there's some unit normal vector n associated with the surface. And then the surface integral of f over the surface S, okay, or the flux of f across that surface S is going to be the double integral of f dot ds, which we define as the double integral of f dot n ds. So it's a surface integral like we've done in the previous videos. And then this quantity represents flux. It's measuring how much fluid is flowing across the boundary of the surface if my vector field f represents the velocity of a fluid. Okay, there are other types of fluxes that occur in physics. There's gravitational flux that has to do with vector fields that represent gravity. There's also electric fluxes. That's for vector fields that represent the electric force. So there are lots of different types of fluxes that can be computed in physics and in fluid flow and other applications. Okay, so the question though is how are we going to find that unit normal vector n? Well, what we can do is we can parameterize our surface. So we will parameterize S by R of UV. So we're going to parameterize it using 2 parameters. Okay, then we know that there is a normal vector, capital N, which is the cross product of the derivative of R with respect to U and the derivative of R with respect to V. Well, if we want a unit normal vector, then n is going to be capital N divided by the magnitude of capital N. Well, what does that mean for the terms f dot n ds? Well, if we do f dot capital N divided by the magnitude of capital N, then we learned previously that ds, okay, can be described as the magnitude of that normal vector du dv. And so this actually simplifies to f dot capital N du dv, because the magnitudes of capital N cancel. Okay, so this gives us a way that we can compute this double integral. We'll have to parameterize the surface like we've done before using, say, u and v, and then f dot little n, actually ds, turns out to be f dot capital N du dv. Now, in most cases when we're computing surface integrals, our surfaces are actually going to be z being a function of x and y. So imagine that we have some sort of vector field f in 3 dimensions. So it's functions p, q, and r of x and y. And then s is going to be the surface z equals f of x, y. So in other words, r, the parameterization is just going to be x, y, and f of x, y. Well, previously we saw that the normal vector in this case was minus z, taking the derivative with respect to x, minus the derivative of z with respect to y, and then 1. Okay, so when doing surface integrals over surfaces z equals f of x, y, we were able to parameterize that surface x, y, f of x, y, and then we were able to see that the normal vector was just minus z sub x minus z sub y, and then 1. Well, then f dot n in this case is going to be minus z sub x times p minus z sub y times q, and then plus r. So when we want to do a double integral over s of f dot ds, in fact, we can do a double integral over the domain of x and y. We'll just call that d for now. And then we're going to integrate minus z sub x, p, minus z sub y, q, plus r, dx, dy. So there's this kind of nice natural way to compute the normal vector when z is a function of x and y. And so this is how we can simplify our surface integral to make that computation.